Hello, welcome everybody to our business intelligence lecture. Today we will start with the very basics of artificial intelligence. Okay, so the backbone of what makes systems intelligent. I call this deep learning by hand. Okay, because we do it with a piece of paper. Deep learning is the basic technology that makes artificial intelligence as we know it today possible. It's a mimic of the human brain and helps us compute information in an intelligent way, whatever intelligence means, okay? So it has a mathematical explanation, and this is what we learn today. After the today lecture, you will do next week some exercises that are relevant for the exam, so make sure you come to terms with this. So basically, imagine we have a neuron, one cell, okay, in your brains, and we try to mimic this neuron mathematically. The neuron gets some inputs. Some information as input, and gets after some computation gives some output. Okay, so this is basically the structure. We have an input, which is some information, then we have a neuron, which is a computation unit, and then this computation unit gives some sort of output, some decision or something like that. Okay. So this is what we are going to mimic now in our system, in our lecture using mathematics. So the analog of the neuron is something called perceptron. Okay. So this is just one neuron. And the way a perceptron works is like this. Okay. So imagine you have certain input units, say x1, x2, xn. Okay, this can be units of information, pixels, stuff like that. This is a vector of input, vector x. This is the input. Then we multiply this input with some weights, which are going to be learned. That's why we call this deep learning. Okay, we are going to be adjusting the weights. Adjust the weights is the same thing as saying that we learn. So we have a weights vector that we are going to be adjusting, we are going to be learning, and what the neuron does is it multiplies, it combines all these inputs with the weights. It adds them up and it adds something called bias. Okay. So, and this has a very, very specific geometric meaning. As always, when we talk, it is important that you not only understand what we do, but you need to understand why we do it, and the best way to understand why we do things is with graphics. So just for everybody, please be on time, okay? So 2 minutes before the lecture starts, you are already online in the lobby, okay? Otherwise, I cannot guarantee that you get into the lecture, okay? So please be on time. So what does this do? This is the neuron. So sorry, this is the weights. This is the neuron or our perceptron, okay? So what does this equation mean graphically? Imagine we do this only for one dimension, okay? Only one variable, one dimension. This is our x sub e. This is the output of our neuron, x sub e, w sub e, okay? What is a function that is x sub e times w sub e? Let me paint here neuron, okay? X sub e times w sub e is a line, okay? Eine Gerade. That goes through the origin. So depending on w sub e, it will be more or less inclined. Okay, so it can be inclined. The inclination is w sub e, and so this w sub e is just what we call the Steigung. Okay. Okay. This alpha, the Steigung, is the arctangent of w sub e. So, and then to make the whole thing more expressive, we add a bias to get out of the condition that it goes through the origin. Okay, so this bias makes us more flexible, so we can learn both w sub e, the weights, and the bias. Okay. So this is what the neuron does. It aggregates the neuron or the perceptron, in other words, aggregates the input the weights and the bias. Okay, but we haven't learned yet. Okay, what this does is it creates an output which needs to be activated by something called activation function. To be computed later, and this is our what we called prediction. Okay, or better said, I put this here, and this is called prediction. Okay, so we compare doch, prediction is richtig. We compare this with our expectation. What we expect it to be. And then we deliver something called error. Which is something like the expectation minus, or the prediction minus the expectation. In order to make it always positive, so we don't have cancellations because of sign, we called this the quadratic error, to make the error always positive. So this is the quadratic error. And of course, we want to minimize this error to make our expectation and our prediction very similar. The error should be so close as possible to 0. So we fit this back into the learning loop. Okay. So we have something called forward process, which goes all the way to here. Okay, this is called forward pass. And we have some learning loop to adjust the weights, and this is called back propagation. Okay. Any questions so far? So let's go through this step by step. Step 1. Step 1 is here. Let's say we paint it with a different color. Let's say this. Step 1 is we multiply all input values x sub e with their weights w sub e, and calculate the weighted sum after the bias. Okay, this is what we already explained above. Any questions on this? Okay, so step 2 is the activation function. Here we apply an activation function to the above giving an output of the form y with hat equal activation function applied to the sum of whatever the neuron is computing. Okay, so this is important because it is going to make computation way easier. So examples of activation functions, I'll give you 2. The first one is the step function. Step function works very simply. You probably already know it. Works like this. Whatever is negative is transformed into 0. Whatever is positive is transformed into 1. Okay. So this is useful for some problems. Not for all problems, but for some problems it's useful. For other problems, we want, this is the step function. For other problems, we have this other activation function called rectifier linear unit. Which can be described like this. Okay, so the rectifier linear unit is 0. Whatever is negative is turned to 0. Whatever is positive remains the same. This is the rectifier linear unit, or also called ReLU. There are many others, okay? There's also ReLux and modified Velux and normalized, and I don't know, there are many. Excuse me. But these two are the most important and the ones we are going to use here. Okay, so the step 3 is going to be here. Step 3. Going to be here. And we are going to calculate we need to learn which weights make the equation y with a hot f of the sum as similar as possible to the expectation. For this, we use the quadratic of the error, which is the difference of the values. Okay, so we defined a cost function C equal 1 divided by 2 y minus y with a hat square. Okay, so the cost function is going to be 1 divided by 2, the prediction minus the sum of x sub e, w sub e plus b applied with f square. Okay, and with that we are going to operate. This is how the perceptron, our first seminal deep learning unit, in action. So explain mathematically. So any questions? Let me see if I get it. So Yeah. All right. Good. So let's do some examples if there are no questions. And you will see that it's not so hard once we start. Okay, so example number 1. Okay. Example number 1 is a single neuron forward pass. Okay, so we have an input vector with 3 elements, 2, 1, and 3. We have a weight vector, 1, -1, 1. Question is, if we apply the function rectifier linear unit, what is the output? Okay. Let's do it. You will see it's not so difficult. I try to do it slowly. If you have any problems understanding, let me know, because this is basic, and after that we increase the difficulty. Okay, so I paint a vector here, then I paint the weight units here. One, -1, 1. Okay, so this is W. So far you can follow. Daumen hoch, Daumen runter. Alles gut. So, okay. So far is okay. So what is now the multiplication of W sub E X sub E? Oh, and of course, sorry, we need a bias. Bias is going to be 5. Okay, so I need a bias here. My mistake, sorry. I paint also the bias here. Good. So what is the result of doing this? Well, this is quite simple. We multiply 2 times 1 x1 with w1, x2 with w2, x3 with w3, and then the bias, right? So 2 times 1 plus 1 times -1, 3 times 1 plus 5. I repeat, 2 times 1 plus 1 times -1 plus 3 times 1 plus 5. Okay. So this is 7, 10, 7, no, 2 times 1, 2, minus 1, 1, plus 3 is 4, plus 5 is 9, right? So the output of the whole thing is here a 9. This is very simple math. Okay, so now we apply ReLU. So the function ReLU to the output. Apply to 9 because it's positive. It stays the same. And this is the output of our perceptron. Okay? Any questions? Daumen hoch oder Daumen runter, irgendein Feedback wäre nicht schlecht. Einfach nicht sagen, ich kann keine Gedanken lesen. Dankeschön. Okay, so das ist jetzt this is our first example. Excuse me, sometimes change to German. Not intended. Natürlich, Fragen können auf Deutsch gestellt werden. So the second example, this was just the easiest form of the second example. Example number 2. Now we have two layers of perceptrons. Okay, so here we only have one neuron, but now we have layers of perceptrons with 3 and 4 neurons each. Okay, so we have now x1, x2, x3. Okay, 3 neurons in the first layer, each one with 1 input. Layer 1, and then layer 2 has 4 and then it will have a vector of 4 units in the output. So here we have a weight from 1 to 1, a weight from 1 to 2, and so on. Okay? You need to understand that the weights are just relationships. So this will be the weight 3 to 4. The weights are just relationships between the input and the output layer. Okay? Is this understood? So this is the problem. The input vector will be 2, 1, 3, and the weight and bias will be a matrix, okay, to transform. So the data is given like this. This will be given to you in case this is asked in the exam. So this is 2, 1, and 3. And then the data, we have the weight matrix, okay, which has the weight matrix has 3 inputs and 4 outputs. So because it has 3 inputs and 4 outputs, okay, so the dimension is 3 times 4. The weight matrix is 3 times 4. It takes an input of 3 and transforms it into an output of 4. This is important for you to grasp. One. And then the bias. Vector given there. So I will write some numbers now. These numbers you can change and train yourself. 1, 1, 0, 0, 0, 1, 1, 1, and then 1, 0, 1, minus 2. So this is the problem, and now we want the solution. I'll paint it with a different color. Let's say like that. Okay. And the solution is going to be like this. So we take the first vector, multiply 2 times 1, 2 times 1, just as we did before, plus 1 times minus 1, plus 3 times 1, plus 5, yields 9, just as we had before, okay? The second, somebody want to do it? Please. No. 3. It's 3. Right? Very good. So we put a 3. Very good. Thank you very much. So what our friend did is just multiply 2 times 1. 1 times 1 is 3 times 0. plus 0. Same thing, okay? What about the third? Somebody want to do it? Okay, thank you. Yes. Yeah. Yes. Yes. 5. Very good. Thank you very much. So again, simple math. I mean, it couldn't be easier, okay? 2 times 0, 1 times 1, 3 times 1, plus 1. Just make sure you don't get lost. And the fourth one, again, somebody want to do it? Okay, if not, I can do it real quick. 2 times 1 plus 1 times 0 plus 3 times 1 plus minus 2. Okay, this would yield 2. 3 minus 2 is going to be 3. Good. So this is our output. If we now apply ReLU, it stays the same because all the numbers are positive. None as done is made 0. So we go out there and say, okay, zack, zack. Our output is going to be exactly the same, 9, 3, 5, and 3. Okay, and this is our output vector. This is going to be I1 with a hat, I2 with a hat, I3 with a hat, I4 with a hat, the output that this layer is going to be giving. Okay? So one thing I am going to say in English and then in German because it's important. This kind of mathematics is not difficult. Okay? As you can see, it's just multiplying and adding. You can do it even without a calculator. This is not difficult. Everyone can do it. Everyone can learn artificial intelligence, okay? It is only up to you that you get into the concepts. Okay? Ich wiederhole es auf Deutsch, weil es ist halt einfach wichtig. Diese Mathe ist nicht schwer. Jeder kann KI lernen. Jeder kann Machine Learning lernen. Es ist nur eine Frage, wie schwer oder einfach erklärt wird. Wie bitte? Bitte macht eure Mikrofone aus, das wäre lieb. Sofern ihr keine Fragen habt. So, ich wiederhole, diese Mathe ist nicht schwer. Das heißt, jeder kann es lernen. Das heißt, es gibt keine Ausrede. Okay? So, no alibi to learn this. Only your own discipline. Ja. Okay. Fragen? Any questions on this second example? This is 2 layers of perceptrons with 3 and 4 layers each. Sorry. So example number 3. Example number 3. We have now 3 layers. Of perceptrons. With 3, 4, and 2 neurons each. Okay, so let me copy the above configuration. I'll just make a little screenshot. I'll copy it and then I don't need to do it again. Save the photos. So then I put it here. I'm going to add it. Okay, so this is the layers that we had. And now I am going to add a new layer. Let me crop it because no, I want to wait. I don't like it. Sorry, I need to do it again. I need to do it again. Excuse me. So here, it's just taking forever. Don't care. I do it again. Sorry about that. So X1, or let's say first neuron, second neuron, third neuron, then 1, 2, 3, and 4, and then just 2. Okay, only 2. So this is the new. Here we will have all connections to, I mean, everybody with everybody. I don't copy everything again because it just takes forever. But this is a fully connected network. You already know what networks are, so this is the weight matrix. This we call the layer 1. This we call the hidden layer. And this we call the layer 2, the output. So the weight matrix we have from layer 1 to hidden, and the second weight matrix we have from hidden to layer 2. Okay. We will have also for each weight matrix we have a bias. So let's repeat the game again. Let's have a new vector with 3 units. Let's say 3, 1, and 2. Then we have a new weight matrix, which is going to have, the weight matrix is going to have a 3x4 dimension from layer 1 to hidden, because the input is 3 and the output is 4. You need to internalize this logic, okay? And then this is a weight matrix. Let's say I say 1, -1, 0, 0, 1, 1, 1, 1, 0, and -1, 1, -1. And we also have a bias vector here with also 4 elements. It's the bias vector 1. Let's say 3, 5, -2, -3. Okay, so which is the output? The output is something like, let's say, something we already know how to do. Let's say 3 times 1 minus 1 is 2, plus 3 is going to be 5. If I make a mistake, let me know. 3 times 0 is 0. 1 plus 1 is 3, plus 5 is 8. 3 plus 1 is 4. Minus 2 is 2. And minus 3 plus 1 is minus 2. Minus 4 is minus 6. Minus 3 is minus 9. Okay, we apply here our ReLU, rectified linear unit, and the output turns to what? Can somebody tell me? Hello? Somebody tell me? Okay, so 5 turns into 5 because it's positive, 8 turns into 8, 2 turns into 2, and minus 9 turns into what? Into 0. Yes, very good, because the ReLU turns everything that is negative to 0, and whatever is positive remains the same. Remember that, okay? Put that into your brains. This is ReLU, this is important. So this is the output of the second layer, of the hidden layer, sorry, the output here. And now we take, so whatever I paint in black is going to be given to you in a hypothetical exam, okay? So whatever I give you black, it's going to be an input. So again, a new weight matrix, which is going to be 4 times 2, because it has 4 elements of input and 2 elements of output. And so 4 times 2. Okay. I just write some random numbers, 1 minus 1, 1, 0, and then minus 1, 1, 0, 1. And then I write some bias, which is going to have 1 by 2, because the output is 2. And then it's going to be 3 minus 2, okay? So what is the output now? You can imagine again, simple as multiplying and adding. The most important thing here is that you don't lose your shit, okay? So don't get nervous, just implement this slowly but steady. So 5 times 1 is 5, minus 8 is minus 3, plus 2 is minus 1, plus 3 is 2. Minus 5 plus 8 is plus 3. 0, 0 plus 3 minus 2 is 1. So if we apply ReLU here, this leads to following result. 2 remains same because positive, 1 remains same because it's positive. So this is the output. Okay, this is the output here. Okay. Are you cool with this? This is not difficult math. It's something that your 10-year-old brother, sister could do. Of course, it gets more difficult later, but right now it's simple. And I need everyone that does not understand it to raise hand and say, hey, I don't understand this step, explain again. Because this is why I'm here, okay? To explain, not to show off. Okay. So, any questions? Irgendwelche Fragen bisher? Möchte jemand noch was erklärt bekommen? Good. I press here pause. Exercise number 4, okay? Exercise number 4 is going to have another additional layer of 3 elements in the end, and we are going to perform not only the feed forward but also the back propagation. So we have another layer of 3 elements, and we're going to have the feed forward and the back propagation. Okay, let me just put together the numbers and then I explain everything. So this is the second weight matrix: 1, -1, 1, 0, 2, 1, 0, -1, 1, -3. So this is the weight matrix H1, H2, and this is the second bias. And then the third one, which will have 2 by 3. Should be around here, let's say. This is the weight matrix H2 to L2, and 2 elements here and 3 elements in the horizontal. Okay, so let's say 1, -1, 2, 0, 1, -1, and 1, 1, 1. Okay, so and this is the bias number 3. So let's put together the example. This is example number 4. So 4 layers. With 3, 4, 2, 3 neurons. With forward pass and back propagation. Okay. So first of all, we do the forward pass. This is the nothing, let's say nothing new under the sun. As I said, everything that is black is given to you in the exam. Okay. so you can easily follow what is given and what is new. So let's do it. 2 times 1, 2 plus 1 is 3, minus 3 is 0, plus 0 is 0. 0 minus 1 plus 3 is 2, plus 1 is 3. 2 minus 1 is 1, plus 3 is 4, plus 3 is 7. And 4 minus 1 is 3, plus 3 is 6, minus 3 is 3. So if we apply ReLU here, we get exactly the same result. Zero, 3, 7, 3. Okay, so in this matter, no questions so far, I guess, right? If you have any questions, just raise your hand, or better, put your microphone on and just talk, okay? I cannot be looking at the camera if somebody raised their hand, so just talk. Again, here the same, 0 times 1 minus 3 is, as a 0 times 1 is 0, minus 3 is minus 3, plus 7 is plus 4, 0 plus 2 is 6. 0, 0, minus 7 plus 3 is minus 4, minus 3 is, no, minus 9 is minus 11. I do it again. 0, 0, minus 7 plus 3, minus 4. Minus 3 is minus 7. Again, 0, 0, minus 7 plus 3 is minus 4, minus 3 is minus 7. So we apply here again ReLU, and we end up with what? Can somebody tell me? 6 and 0. Very well. 6 and 0. Okay. So we, well, let me put it a little bit closer to the left. So we're going to need a space. 6 and 0. Very well. So we are cool now. 6 and 0. So here we go ahead and we continue with the same shit. Okay, so now you need to pay attention. 6 times 1 is 6. 0 plus 2 is 8. 0, 0 minus 1. 6, 0 plus 1 is 7. Good. This could be the output and we could apply ReLU, but now in the last layer, this is super important now, okay? Here, I'm going to be putting numbers to give you hints, okay? If in the last layer, before back propagation, if we do the fast forward, it's okay. But if we want to learn with the back propagation, we need the elements of the vector of the output vector to add up 1. This is because they are representing a probability distribution. So in order to do that, we apply the so-called softmax function. So the softmax function applied to 8, -1, and 7 works like this. In order for these elements to add up 1, we take the first element 8, then 8 plus the absolute value of -1 plus 7, then the absolute value of -1 divided by, again, 8 plus absolute value of -1 plus 7, and then 7 divided by 8 plus the absolute value of -1 plus 7. This is 8 divided by 16, 1 divided by 16, and 7 divided by 16. This is not very difficult to do. You can do it in your head. 0.125 and then 0.375. Okay. This is the way to apply a softmax function to a, so here we apply, before we continue, we apply softmax. And what we get is a distribution of the numbers. Zero 0.5, 0.125, 0.375. Okay. Maybe I did it wrong in my brain. Wait. 1 divided by 16. You're right. Yes. Sorry. Thank you. Thank you. 0.625. It was even smaller. 0.43. Thank you. 43.7. So let's change it. Thank you again. 0.6 and then 0.47, let's say, or 40, 43, 44. Okay, so this is the output. Also, I will be giving you the prediction, which could be maybe something like, the prediction could be something like 100. So our prediction is that that the first position is going to be the one being on top. Okay. So the first thing we do is we do the error. We calculate the error. And I will paint this in blue. The error is going to be then what? Can somebody tell me? If we subtract these two numbers, minus 0.5, this comes from 0.5 minus 1. then 0.06, and then 0.44. This is the error. We call this error number 3. Okay? Are you cool with me right now? So, the second thing you need to remember, I put a number 2 here, okay? So you have a legend here, down here, so you can always look. The error, and this is important, okay? Just, I mean, this is new for everybody, so it's equally difficult or easy for everybody. So the error, now we're going up, okay? The error becomes the bias of the previous layer. And this is the key concept, or one of the key concepts that we use in deep learning. So this error is going to become the bias of the next previous of the previous layer, okay? So we put this error up here. This thing goes up here, and it becomes the new bias 2. Okay, so we just copy the numbers. Just copy the numbers. Minus 0.5, 0.06, 0.44. All right? So we're just putting these numbers up there. So that's no big deal, right? Es ist nicht schwer. Oder hat jemand da ein Problem? Good. So the next step, number 3. In the step number 3, we perform an element-wise multiplication of the new bias and the output of the layer. Okay, so what does it mean? Element-wise multiplication. It means that we do the following. We do the following. We multiply 6 times 0.5 and put it here, element-wise. 6 times 0.5 is -3. All right, this is 0.36. And 6 times 0.44 is 2.64. Everything multiplied by 0 is 0. Okay? Sorry, this is bias number 3. The new bias here. And what this is this is the updated weight matrix. This weight matrix is this. Okay? So this is the third step. The fourth step we need is we calculate the new error for the previous layer. Is obtained by multiplying the new bias with the old weights. It's a multiplication. It's not an element-wise multiplication. It's just a multiplication. So I do this in a new color. Let's say light blue. Okay. So now we multiply. We multiply the new bias with the old weight matrix. So let's say what we get minus 0.5 times 1. It's minus 0.5 times 1. Later on you have the video so you can go ahead and look at plus 0.06 times 0. 0.06 times 0 plus 0.44 times 1. Okay? And this is going to deliver 0.06, I guess. Minus 0.06. So minus 0.06. The other one, minus 0.5 times minus 1 plus 0.06 times 1 plus 0.44 times 1 equaling 0.06. 0.5 plus 0.5 equaling 1, I guess. Okay. So this is going to be the new error number 2. Okay, so this is this part, and this is this part. Can you follow? And the rest is just the same. It's just performing exactly the same calculations, more or less automatically. So this is the new bias, the actualization of the bias, minus 0.06, 1. We can get again results up here. So we just get the new numbers. This is an element wise. Remember, element wise means you multiply element by elements. This means this is 0, 0, minus 0.18, 3, minus 0.42, 7, minus 0.18, 3. Okay, so and this is the new weight matrix H1, H2 star. Okay. And then you get the new, yet another color, the new error, which is going to have 4 elements, 4 elements. The elements will be calculated by 0.06 in minus plus 1, so 0.94, 0.06, minus 106, and 1. And this is the error, then error 1. Which in turn will be the new bias. This is the new bias. Just copy the numbers up there. (0.94), 0.06, minus 1, 0.6, and 1. And then we get the new weight matrix, which would be then updated . Okay, so 0.94 is multiplied by 2 is 188. 0.06 is 0.12, versus minus 212 versus 2, 0.94, 0.06, minus 106, 1, and 0.98 times 3 is 282, 0.18, 106 times 3, 318, and 3. Okay, so this is the new weight matrix L1 H1 star after learning, and this is the new bias vector after learning. Okay, so, and this is the way the cookie crumbles. After this, we would substitute this here, substitute this here, substitute this here. Of course, you need to transpose it. Substitute this here. You see they have the same dimensions. You substitute this here, substitute this here, and then turn back again, and so on and so forth, so back and forth until you get a minimum error. We want to minimize this error. Okay. Okay, any questions? So basically you have learned today the basics of deep learning, okay? And this is the very basics of all intelligent agents that you are using in a daily basis in your ChatGPT and how you call them, whatever you call them. So this is absolutely important for your exam. So make sure you learn this really well, and make sure you practice, because this is going to cost you points if you don't do in the exam. All right. Any questions?